Hi, everybody. Welcome, developers of Earth. We have another good webinar for you today. My name is Khalid for JetBrains, and today I'm really excited for the talk that's happening today. But before we get to our guest today, let's go through some housekeeping. So first of all, this is on YouTube. So if you're watching this directly on the YouTube page, you'll notice that there's actually a chat there. If you want to ask any questions and if you have any good ideas or thoughts or comments, please leave them in the chat and we'll try to get to them. If you have specific questions for our guest today, I'll try to pick some of the best questions to ask Steve by the end of this webinar. One of the common questions asked during these webinars is this recorded? And yes, it will be. It will be made available on JetBrains TV. So be sure to like and subscribe to get the latest recorded videos there. So short of that, I'd like to welcome our guest today, Steve. Steve is going to be talking about profiling and fixing problems in production. Steve, welcome, and I'm really excited to talk to you today.
Thanks for having me. I'm really excited to talk about this because it's one of my favorite things.
Yeah, it's I was looking through your profile, and you kind of have a prolific understanding of languages. You kind of seem to have done it all, and it's really neat to kind of see that. But today we're really focusing on .NET. But the other thing I noticed in your profile, you have pop punk dev, and one of the things that got me curious is like, what is your favorite pop punk band?
Yeah, so I created that hashtag because it started with DevOps, and then you added security into that, and it's DevSecOps, and then it's like, well, what about networking? What about business? And so this hashtag got longer and longer. I'm like, well, why not Dev Pop Punk Ops? Because I'm a big fan of pop punk. I think if I had to choose one, I would probably choose the Wonder Years as my favorite band.
Oh, that's a good one.
But yeah, there's just so many right now. The scene is in a good place. So Neck Deep, Real Friends. Yeah.
So very
lots of good stuff.
Yeah, I like Newfound Glory. They're probably my favorite band from that era of pop punk. But we're not here to talk about pop punk, right? We're here to talk about fixing problems. And I think for me, the thing that's really exciting about this talk, and hopefully you get into this, is like JetBrains offers a lot of profiling tools, but most of the time people don't reach for them until, horrible, terrible things are happening in production, right? So hopefully you can show people how to use our tools, how to understand them, and how to fix their problems, even maybe before they become huge catastrophes. So short of that, I'm going to give you the stage. I'll be on here, but I'll be super quiet.
All right, thanks. So welcome, everyone. I'm glad to be sharing one of my favorite things with you all today. So as Khalid mentioned, my name's Steve. I've been a professional software developer for almost 2 decades now, working at a bunch of companies full-time, then doing my own thing as a consultant. I now lead an open source software company called Eco APM, which focuses on application performance. These are all the ways you can find me online. No need to screenshot this or write it all down. You'll be able to see it again at the end. What are we going to talk about today, right? In general, performance, but more specifically, first, we're going to go over latency and bottlenecks and some definitions, profiling and profilers, what they mean, what they do, how they work, etc. The majority of this morning or this afternoon, depending on your time zone, is going to be spent hands-on. So I have a demo app that I'll show you, and it's pretty slow right now, and we're going to make it faster. So that's going to be the big chunk of it, and then we'll have some time for Q&A at the end. But also, if there's specific questions throughout, there are a couple spots where we can take a pause and answer anything specific to what was just talked about. While a lot of what we're doing is going to be C# and .NET, in C# and .NET, a lot of the patterns and practices that I talk about are they hold true everywhere, regardless of language or framework. So I'm hoping you can come away with some more general ideas for how to improve performance in your app. But first, why should we care about performance? So I've got 5 reasons here. These are not the only ones. These are just 5 that I chose to highlight. So first of all, user experience, right? If you look around on the internet, you'll see numerous studies about how introducing artificial latency reduces sales, reduces engagement, reduces user happiness. Removing that latency increases sales, increases user experience, happiness, etc. So there's a direct correlation between the performance of your software and the user's experience with it. Accessibility, not just talking about your typical accessibility concerns, but also economic accessibility, right? The heavier software becomes, the less lightweight hardware can handle it. So this is my phone. It's 4 years old at this point. It's my primary internet surfing device, and there are several sites that I just can't access on it because they're too heavy. It takes minutes literally to load a page, and that's just not great. So we want to make sure that everyone who wants to access your stuff can get there. Hosting costs. This one's more like why your company should care about performance. It's about the bottom line, right? Less scaling required, lighter hardware requirements for the server side. Basically, they're paying less money to run the software. Planned obsolescence is a pretty big problem these days. There's so much hardware and technology going in the trash because it's outdated. And the planet has finite resources, right? We're eventually going to run out of these rare earth minerals that are needed, which is going to drive prices up. It's going to make those who are, on the lower side of the economic accessibility spectrum, it's going to make things harder for them, right? They can't afford hardware. Look at what's happening with video cards right now because of the Bitcoin boom. Don't even get me started on Bitcoin, because as mentioned in the last bullet point here, energy usage, right? This is kind of where I've chosen to focus my company on, because software is eating the world and it's using vast amounts of electricity. And there are less than 10 countries on the planet that get the majority of their electricity from renewable energy. So your software is burning fossil fuels, right? And we want less of that because we know that fossil fuels are destroying the planet and we need to live on this planet. So let's try and keep it clean. There's 2 main metrics when we're talking about web performance: latency and throughput. So latency is how fast you can return a response. It's measured in seconds or usually milliseconds. We're hopefully going to get into microseconds today. We'll see how that goes. And the reason we want to focus on latency is when you do that, you get throughput for free. So throughput is about how many responses you can return, often measured in requests per second. If you go to the Tech and Power benchmarks, you see that the top frameworks all have throughput in millions of responses per second. Most real-world web applications are more on the order of, hundreds or thousands. But if you focus on throughput, the way to increase that is usually scaling out, right? Throwing more hardware at the problem. But that adds complexity. You need a load balancer, you need other networking gear, etc. So focusing on latency, you get that extra throughput for free because it takes less time to handle each response. Here are some numbers just to kind of get into understanding the size and the scale of certain things. So a CPU instruction these days takes about half a nanosecond. If you multiply this by 2 or 3 billion, you get about a second, and that's, gigahertz, right? We have 3 layers of caching in most CPUs these days, L1, L2, L3. You can see that they kind of take increasing amounts of time to get there, but they also increase in size. We're not going to deal specifically with this. It's a little too low level hardware-wise for this talk, but just know that those things exist and that your CPU is trying to store things within the CPU that are used often so that it doesn't need to go to somewhere slower to get them. Because you can see, RAM is about twice as slow as the L3 cache. But as soon as we jump to hard drives, that's a huge jump, right? 30 nanoseconds to 30 microseconds. That's 1,000 times slower. It's 1,000 times slower to get something from your hard drive than it is to get from RAM. And so that's going to be a big point that we want to remember when we're working on this app that we're going to fix up, right? Even slower than that, trying to get things over a network. Here I have my Raspberry Pi. This is usually my load generator when I'm doing load tests. And it takes about a millisecond for data to get from the Pi to the switch in the closet, to my desktop, and back again. And kind of extrapolating upon that, the internet is, the same thing, just a lot more wires and a lot more devices. So the Azure backbone from their US East to US East 2 facility, they have that benchmarked at 6 milliseconds, which they're literally right next door as far as the internet's concerned. But that's how long it takes, right? Unfortunately, we can't increase the speed of light. So the farther data has to travel, the longer it's going to take, right? Things that are going halfway across the world could take up to 500 milliseconds. These are all, fine and dandy numbers, but humans have a hard time with very large and very small scales. So some of that might not, really hit home. I've scaled this to a more human time scale where a CPU instruction takes 1 second, right? You can see that getting things from the CPU cache is on the order of many seconds. Getting stuff from RAM takes a minute, right? And then here's where the huge jumps start to come in, is that getting stuff from a hard drive takes 9 hours. From a LAN takes 12 days, and over the internet takes 10 weeks. So if a human being was a CPU doing one thing per second, right? These times are absurdly long. And so from these, huge gaps between the local stuff and the remote items here, we really have two types of bottlenecks, right? We have CPU bound, and this is all about algorithms and memory efficiency, especially in .NET and other managed runtimes where there's garbage collection, et cetera. And you have I/O bound problems, I/O standing for input output. And the way we solve these is really about efficient offloading of asynchronous tasks so that the CPU can keep working on other important things while it waits for that data, right? If you think about how much time it takes to get something over the internet, right? If you think about like a container ship going across the ocean, if you want something ordered and it's coming on a boat, you're not just going to sit there and wait and do nothing until that thing arrives. You want to, find something useful to do in the meantime. So there's different solutions for each of these problems, and we're going to go through each of them. But how do we know what is slow, right? How do we know if we have a CPU-bound problem or an I/O-bound bottleneck? And that's where profiling comes in, right? There's lots of different ways, but profiling is one tool in our toolbox of figuring that out. So what is profiling? Profiling is the act of measuring CPU time and or memory usage during when the code is actually running. We're going to be focusing pretty much exclusively on CPU time today. Memory usage will come in kind of as a sidebar. But again, we're really focusing on latency and how fast we can make this. So why do we want to profile? Because it gives us easy access to all the data that we need about what's happening in the code as our application is running. How do we do it? In .NET, there are API hooks, which third-party tools can use to aggregate and report on that data. The third-party tool we're going to use today is called .trace. It's JetBrains' profiler. It's my profiler of choice. And it has 4 different ways that it can measure the things that are happening inside the app as it's running. So sampling is literally sampling every couple milliseconds. It's going to check on the call stack and say, hey, what's going on? It's going to record that so that we can look at it later. It's the least intrusive of the methods, but it also provides the least detail. On the plus side, it can connect to an already running application where the others cannot. So that's definitely a bonus. Tracing is kind of a middle ground where it records whenever it enters and leaves a method in the stack. And so that gives you some more information, but it also takes a little more time to gather that information. Line by line has the most overhead, but it also has the most details. So it is recording every line of code that is running and how long that takes. And so, that's going to be really important later on. But we'll also notice that there's about a 10 times slowdown when we're profiling using line by line. The timeline profile is where we're going to start today. It's similar to sampling, but it also captures the order of events that happen, and therefore it's the best way to show async and await details, which, as you'll see, are important early on with how slow our app is. So we're going to go over what this app is that I have created for us to play with. We're going to profile a slow page in the app. We're going to improve its performance, and then we're going to repeat 2 and 3 again. And then we're going to repeat 2 and 3 again. So the app, as I mentioned, my phone is about 4 years old, right? A couple years ago, I dropped it. And so it's been held together by packing tape for a couple years, which means I need a new phone. And as a software developer, I'm not just going to go on some websites to compare phones. I'm going to create my own solution. So we have a whole bunch of, if my app was running, we would have a whole bunch of phones here to look at. Most of them, of course, are not real, but we do have a couple of real phones. And so I can select a phone to look at, and if I ever actually see what's going on, we can see some information. So this is our slow page that we are going to profile and fix, and it may seem absurdly slow, especially given how much I'm talking while we wait for it to load. But there are many pages in the public, here we go, that are this slow. So the local grocery store, when I try and sign in the grocery store so they can scan my QR code so I can get my discounts, that takes 20 seconds to log in. My health insurance provider, when I do single sign-on with them, it takes 24 seconds to log in. So these things exist in the wild. It may seem absurd, especially if you're kind of performance inclined to begin with, but it's not, out of the realm of possibility. And I think it's a great place to start because there's a lot of low-hanging fruit for easy improvement. So here's our page, right? That took a long time to load for not a lot of useful information. So what we're going to do is we are going to profile this. Why is it slow, right? So here's the main page of .trace. When you start it up, this is what you see. Basically what we need to do, we need to choose something to profile. We can choose how we want to profile it, and then we want to start it. So I've got my app running, right here, this phones.exe here. We want it to do a timeline profile because this is so slow that I think that there's some asynchronous funkiness going on. And we want to make sure that we're collecting TPL events. So this is going to give us all our async await data in a more consumable fashion. So I'm going to click the start button here. We're going to see it start. We're going to see this little window here saying, oh, I'm ready to go. So I'm going to refresh the page. And we're going to wait another, 20 seconds, unfortunately, while this loads. But while this is running, the profiler is off collecting data about what's going on behind the scenes within the application. Once the page finishes fully loading, we're going to grab a snapshot right here using this button. There we go. And that's going to open up the timeline view in .trace so that we can have a more visual representation of what is going on in the code as the page is loading. So in our timeline view, we have 3 kind of panes left to right in the default layout. On the left, we've got some filters, and it's also some useful information, right? We made one request, and that request took 27 seconds. Wow, okay. In the middle, we can see kind of a graph of all the different threads that were part of that response and the CPU usage during that time. So if we zoom in here, I'm scrolling up, you can see that CPU is busy during the dark periods and the CPU is not busy during the gray periods. So there's a lot of just idle waiting happening right here, all this gray. When we hover over a certain time on a certain thread, we can see what's going on. So we can see the thread state is running here. There's a whole lot of waiting everywhere else in the thread state. On the right here, we have our call stack. And this basically shows up top the hotspots, or, here's where the CPU is being used the most. And on the bottom, we have the call tree, which is kind of basically like a tree, well, yeah, of all the calls that were made. So because we know that we have an async issue, right, we want to look for this async keyword here, and we can find that this info method on our home controller is likely the culprit, right? Also looking at the URL, the app uses a standard routing pattern, right? So home info right here matches up with the home controller's info method. We want to check our continuations and our awaits checkboxes here. A continuation, just in case you're not familiar, is the callback essentially of what happens after an await. So when you await something in your code, the CPU waits for it to finish, and then something else happens afterwards. That afterwards is the continuation. So we can see here that 27.5 of our 27.6 or 7 seconds is spent awaiting. And when we highlight this method, we can see, based on these black boxes, where the CPU is actually busy as part of that. And everything that's not highlighted here on these threads is when the CPU is awaiting a task to complete. So that's a big problem, right? We've got loads of wasted time here. How do we fix that? Well, we have a problem, right? We're doing a bunch of things and we're doing them in serial. Let's get rid of this. So here's an example of 32 tasks. We're doing them all in order, right? That takes a lot longer than if we were to split it up. So you can see in the examples halfway down, we've got 4 workers, let's call them, doing 8 tasks each. We can complete our work 4 times faster because we're splitting it up. We could also split it up into 8 if we have enough workers, or if we have 32 workers, also known as CPU cores, we could be doing 32 different things at a time, right? And then everything finishes really quickly. Note that the order doesn't matter here, right? As long as we get all our numbers, we're good. Certain times the order will matter, but we're not concerned with that immediately. The way we do a lot of task parallelization in .NET is with async await. Those of you familiar with .NET will be very familiar with async await, especially over the last few years. But the keyword actually exists in many languages now. This is kind of a chronological list of who got it when. So it started in C# and F#, Haskell and Python got it after that, TypeScript and JavaScript. I was actually surprised to learn that as of about a year ago, Perl has async await. So, it's everywhere now. It's the new way. It's great for simplifying code and hiding complexity, but it's also great for easily leaving performance on the table, especially when you are asyncifying. What is asyncifying? Well, it's when you get all excited and you're like, yeah, let's do this. So you sprinkle your async await keywords all throughout your code. If you're that type of person, you add the async suffix onto all your method names. I'm not that type of person, but I won't judge. Right? So all these things are great. We've unblocked our thread so that the CPU can do other things while it's off doing this slow I/O work. But it's not necessarily good enough, right? As we're about to see. So here's an example, and this is a simplified example of what our app is actually doing. So we've got this for loop, right? And it's going through 1 to 5. And inside that for loop, it's awaiting a result. We don't know or really care what that result is. We just know that it's slow enough that, that we're creating a task for it. So the problem with this is that as the loop iterates, so x is 1, we await our result, we add it to the list. X is 2, we await our result, we add it to the list, right? Even though we freed up our CPU while we're awaiting the result, we're still not making use of our multi-core CPU, which almost all CPUs are these days, right? We've got this await in the loop, therefore only one of them is happening at a time. So what we actually want to do is we want to split off all these tasks simultaneously. And then once they're all done, that's when we return our results, right? We wait for them all to come back, and then we return the result. It's not, here, number 1, you do your thing. Oh, thanks. Here, number 2, you do your thing. Oh, thanks. It's hand out all the cards. Everyone do their thing. I'll wait for everyone to come back. And that way they can all happen at the same time, and we're not wasting time waiting. Note at the bottom, .NET has, or .NET 6 has a new method, parallel, for each async. I wasn't about to YOLO this presentation on .NET 6 yet, so you can experiment with that on your own. So let's find this in our code and see what the problem is. So right, we saw in .trace that our home controller's info method was kind of the entry point and the point of slowness, right? And we can see here we have a for each loop. And inside that, we're doing some awaiting. So what we're going to do is, let's pull this out into a method first of all. All right, so we're going to get our price view model. But what we actually want to do, instead of doing that in the for loop, is we want to get our phone info, right? And for each of those, we want to get our view model, right? And yes, we want to use the method group because that's going to make it look nicer. Notice that we have a list of tasks here, right? It's not a list of the view models, it's a list of tasks. And then our prices, instead of going through the list in a for each loop, what we want to do is await when they all complete. And that when all method then returns the T or the results of those. So we can get rid of that for loop, right? Great, so we just parallelized all that. The 4 stores that we're getting this price from, we are now doing in parallel. We're not saying, hey, go to the first one, okay, get the result. Okay, go to the next one, get the result. We're saying, hey, everyone, give me your prices. And then it comes back. So that's built. We can see when we refresh this page, it's not going to be absurdly faster, but it's going to be faster. And we can confirm that with our profiler. So as that finishes, we're going to select phones again, another timeline, collect TPL events. Is this ready to start right away? Yeah, we're ready. We're going to start it right away. We're going to refresh while it's collecting its information. Then we're going to check our timeline again. This may seem a little tedious, especially when the pages are so slow, but similar to any sort of refactoring, you want to be taking small steps to be making sure that you're not introducing any other sort of problems or regressions along the way. So our page reloaded, I'm getting the new snapshot. .trace is opening. And we can see here, once this loads on the left, compared to our original 27 seconds, our response was now been in 17 seconds. So that's a decent improvement, right? We can also see that the number of threads has increased, right? We're doing more at once So more work is going on simultaneously. If we look at our info method again, including continuations and awaits, we can see that a lot of those sequential things are no longer happening, right? They're happening all at the beginning and then a big one at the end. So that's good, right? Where there's an improvement. We've almost doubled the speed of our page, but we still got a long way to go, right? There's still something sequential happening here where it's waiting a long time before it's doing something else. And you can see from all the gray here that a lot of that time is just spent waiting for a result. So one of the other things that if you caught it, if not, I'll show it again. You can see that when we're creating our new object here, right, we're awaiting sequentially within the creation of that new result, or in our case, it's called a phone view model. What we actually want to do is similar to before. We want to be pulling out those tasks ahead of time so that they can happen in parallel, right? And then we await the result of those tasks. If we're up here, up top, right, these happen sequentially. We await the result of getX, and then not until that happens do we await the result of getY. You can see here, right, that we're doing this exact thing in our price view model method that we did. So I'm going to extract some variables for not the whole thing, but just the method call here, right? And you can see the type of these. It's a task, it returns a string, a task that returns a decimal, right? And then in our instantiation, that's where we await them. That way both of these things can be happening in parallel, right? And then once they're both done, that's when we create our view model. Round 3, right? Starting up our project with our new code change. Getting ready to start. .trace. Notice I unchecked the create from start this time. And so that's because we want to make sure that we're up and running and everything is good before we actually profile. So I didn't check that box. So instead of immediately getting this get snapshot, we now have a start button. So if you need to get to a certain page before you want to start your profile, you do that. Hey, that didn't look so bad. That looked pretty fast. So we're going to start. We're going to refresh. And once it's done, we're going to get our snapshot. And compared to our 17 seconds previously, we can now see that our request took 10 seconds. So we're slowly getting there, right? 10 is still too long, right? Ideally, we should be less than 1 second per response. That's kind of my baseline benchmark for good response time is less than 1 second. Ideally, it would be much faster than that, and we'll get there. You can start to see even here in our timeline, there's more blue happening, right? This is good. More of a percentage of the time we're spent working on this response is spent being active, right? We're turning our IO bound problem into a CPU bound problem. And as we saw from that list of latencies, CPU bound problems are much faster than IO bound problems. So if we look at this with our continuations and our awaits checked, right, we still have the same things. If we were to zoom in before, we would see that there was actually 2 things happening instead of 1. But we can see, right, 10 seconds instead of 17, we're on the right track. But what happens if parallel tasks are doing the same thing under the hood? Here's a good example of that, right? We have our getX and getY from the previous slide, and we're awaiting them. But behind the scenes, get X and get Y are doing the same thing, right? So what we actually want to do is pull out that get value method ahead of time and just take the X and the Y from that. I'm going to use my magic presenter skills and do this automatically because this is a larger refactor, and I don't know if anyone actually wants to sit and watch me do that. So magic.
It kind of reminds me of cooking shows where there's like a second oven and they pull the fully cooked turkey out. So movie magic.
Yes, exactly. So what I did, I pulled out this price view model method into a price display service, right, which was doing most of the work before. But now we're getting the document once, whereas both the logo and the price before were each traveling to the internet to get the information, coming back, and then dealing with that, right? So we're making half the requests, we're analyzing the response half as often, because that analyzing only takes a very small amount of time, right? It's a CPU bound problem versus the getting of the information is an async bottleneck. We're not going to see a big improvement in time here, but we are going to see reduced CPU usage. And that's beneficial because that allows more CPU opened up for other requests to happen, right? I'm the only user of this app right now, but what happens if I make this a public site where everyone can compare phone prices, right? And we're getting more than one request at a time. The less CPU that's used for me means more for everyone else to share. So that's what that did. Because it doesn't change the profile at all, we're not going to go through the profiling again. You'll just have to believe me. Hopefully you believe me. But everything we've been doing so far is all about dealing with async await. So I think now is probably a good time to take a break so I can have a sip of water, and I can ask Khalid if there's been any async await specific questions in the chat yet.
Well, I think one kind of centers around task when all. I know folks are maybe wondering, like, what's the timing when you have an innumerable collection of tasks and you do a task when all? Does it return immediately when the first one comes back? Does it, like, what's the behavior, I guess?
Yeah, that's a good question. So with the when all method, it waits until they all return their value, right?
Mm-hmm.
I believe, let's see if I can find it again. All right, so we have our when all. I believe there's also a when any.
Mm-hmm.
So when any is, okay, I got my first one back. Now I can start doing something at least, right? And you might be able to work on one of the things, right? Maybe not all of them, right?
Mm-hmm.
Like I'm doing a for each loop right afterwards here, right? We could kind of say, oh, the first one's ready. I can get started on that. And then once the next one's ready, then I can work on that one, etc.
Yeah, and I found, like, when you can use when any one of the results is something you want. So you're kind of competing for the fastest returned result, and you just need one. So
yep.
It's kind of a good strategy, but when all is likely the one most people are going to use, right?
Yeah.
Yep.
Yeah, it's definitely the simplest or the most straightforward, at least.
Yeah, I think people are loving the slides too as you go through the CPU time, or like computer time versus human time. That's been really cool. So I'm a big fan of that. Also, like the distinction between CPU, RAM, and I/O, and thinking about those problems as well. So other than that, there's not really a lot of questions, but there are a lot of viewers, so everyone's still pretty engaged. So good stuff.
All right. Let's see. There we go. All right. Interlude over. Time for a pro tip. And this one's probably pretty straightforward, pretty common sense, but use the best tools for the job. So if we go into our profile here, we can see that a lot of, let's see, where do we want to be? In our continuation. Price. You know what? Let's clear all these out. We got a lot of old data here. We want to get rid of all these old windows. We're going to switch it up from a timeline profile to a line-by-line profile because that's going to give us a lot more information about what's going on. So we can actually do this as well. We don't need to be running just the standalone .trace application. We can do this from right within Rider. So we've got this little button up here right next to our run and debug buttons. It's got a little clock, right? And we can choose our profiling method right here, right? We're going to do line by line because that's what I said. In the configuration, we can choose whether we want to collect it from the start or not. We're not for now, just so you can see the start button that I had before. So we run a line by line profile. We can see it's getting ready. We've got a little window here similar to our pop-up from the standalone app. So we can start recording here when we're ready. So we've got our page ready to go. I'm going to start recording just like before. I'm going to refresh our page. And then we can get our snapshot right within Rider. So the snapshots show up over here. You can take multiple ones if you want, and they'll show up in a list. We can right click. We can either open it in Rider or in standalone.trace. I'm going to keep using standalone because that's my preference. And when we open this, we're going to see a totally different window now, right? Because we're doing a different type of profile. So this is a line-by-line profile. We have some different views on the left here that we didn't have before, and we have a legend. So the threads tree, not my cup of tea. The call tree is the same call tree we saw before, but we have more space for it now, so we can see what's going on. When you're using an ASP.NET Core app, your actual work is going to be in these other threads, not in the main thread. The main thread just runs main and waits and listens for connections. So you want to open the others up to see what's going on. So we can see we've got Angle Sharp, we've got Dapper, right? These are some of the libraries that we're using. But what we actually want to look at here is our plain list. And this is my favorite part because it gives the most information. And it's basically a big table of everything that's been called during the request. Not just what was called, but how many times it was called, and how long the calls took on average, how long the calls took versus what their children took time-wise, right? The percentage of that. But we can see here, right, from the start, by default, it's sorted by total time. From the start, that Angle Sharp has taken up a huge amount of our time, the most time, in fact. So if we were to go and inspect our code, we can see that our price display service, when we get our document here, right, this is using Angle Sharp's browsing context to get the data from a given URL, to parse that data into a document, and then return that document. But in ASP.NET and .NET, as a whole, we have the HTTP client, which has been, I don't even know the word, but there's been so much work that's gone into that to make sure that it's fast and efficient. So what we're going to do is we're going to swap out Angle Sharp for our HTTP client, so that way we can see a better separation of how long is it taking to actually download the data versus how long is it taking to parse the data. And that's going to give us more fine-grained information about why what we're doing is slow. Technically, we can see that from here, right? We've got our HTML parser versus further down. Way further down is the actual request. So we know that the request doesn't take as long necessarily, or sorry, the parsing doesn't take as long as the request, but we know that the HTTP client is faster. So we added our HTTP client to our dependency injection here. So we're going to add it as a dependency here. We have a client factory, and this is how we do this in .NET to make sure that we are using things correctly. We're going to refactor a variable here to get a HTTP field, and we're going to, in our get document, create a client so that we can actually make the call. Create the client. And then the HTML, or actually let's call it the response because that's what it is going to await the client getting the URL, right? And that's actually what we want to return. This changes the type from an I document to an HTTP response, which then means we need to get the document from the response. I'm going to do my get magic again because this is not a live coding pleasant example. It's a larger refactor. Good. Okay, so pop, just like we did before, right? We create the client, we get the result, and then we get our HTML from here, and then we pass that in to our get price, just like we were doing before. Let's profile this and see how it's changed. Profiling from the start has been turned off so that we can make sure that our page works before. And I just realized I forgot something else behind the scenes. Sorry about that. Let's try it again. Ignore the person behind the curtain. So we have our code. It's reloaded. Okay, that looked faster, right? Was it actually faster? So back here, we're going to start recording. We're going to refresh our page. We're going to get our snapshot. Let's check it out. So back in our plain list, we can see and we can compare. There's actually a compare function within .trace, so we could compare against the other one if we wanted to, and we can see what's faster and what's slower. But we can just do this by hand, right? We can see, right, before it took 2.6 seconds, right, 26,000 milliseconds to do this navigate async. Over here, because we pulled that out, right, our biggest method being called is now half a second. So much faster than it was before. We're using a better tool for the job, right? We're using HTTP client instead of Angle Sharp to do our actual fetching of the data over the internet. Angle Sharp under the hood uses web request by default, which I think is like the old convention. New convention, much faster. So excellent. Our page is now under a second of response time, right? Which is getting into the good category. Making sure we went over everything. Good. Okay. Next pro tip is to profile your unit tests, and not just profile your unit tests, but regularly profile your unit tests, right? Khalid was talking early on about how often profiling is more, oh no, like production's on fire, everything is slow, let's fix it. This is one easy way to be really proactive, right? Because I'm assuming you're running your unit tests fairly regularly to begin with. So why not profile them regularly as well? This is also going to help with your development flow, because if your unit tests are slow, that's going to slow you down when you're developing. The faster your unit tests are, the tighter you can make that inner development loop that everyone talks about. So let's do that, right? We can do this as well from right within Rider. So let's pull up our unit tests. Right, we can see they all pass, good. And under here, right, just like we can run all our tests, we can run all our tests with coverage, we can also profile them all. So let's profile our tests. We want to profile them line by line because we can see all the details then about what's going on. Same as when we profile our app, we get this little tab over here. We can open up our profiling.trace and we can see what's going on while our unit tests are running. Digging right into the plain list, because that's my place to go. We can see that getting the logo takes a long time. That's interesting. When we're not doing a timeline profile with the TPL checked, the continuations show up as these method something something move next. So this is the part that happens after the await, or if you're thinking about it like a promise, it's like the callback part of the promise. So we can see, as we dig in through the call stack here, what's taking the most time? Well, mocking is taking some time, of course. But when we go in to get our price view model, right, then we dig into that's continuation, get the price. Let's dig into that continuation. Getting the HTML price to get into that continuation, right? We can still see that Angle Sharp is taking up a lot of time here parsing the HTML. We don't really have much control over that because it is a third-party library. We already replaced part of that with another external class that was faster. But something I want to show instead of focusing on the amount of time that things take is all of these columns are sortable, right? We can sort by the number of calls that are happening. And that means we can see if things are happening more than we should have happened, right? I have how many tests here? I have 9 tests. So, this tens of thousands of database calls happening, that's questionable. So what we want to do here is this is our most called thing. We want to find out where it's called, so we can open the current method instance. And now notice these buttons have changed a little bit, right? Instead of the thread tree and the call tree, we have the call tree and backtraces. And what backtraces does is it shows you where something was called from. So we can kind of reverse up our tree and we can see why things are being called the way that they are. This one is not particularly interesting because it's not our code, but this one is our code and it's the most called method of our code. So let's find out why. We can see that most of the calls are coming from Dapper where we're mapping something. Why are we mapping things so often? That's a good question. So let's check out right here our phone info service get all method. The phone info service is where we get the info from the database. Basically, here's the phone, here's the store, here's the URL that page is at, etc. And we can see here that our get info method, right? If we're getting a single phone's information, we're getting all the phones and then filtering in our app. Why would we be doing that, right? I know some of you may be scoffing at this, but this is actually quite common, right? All the things I'm showing you despite potentially seeming like very obvious things, these are common things that I've found throughout my years, and kind of the easiest ways to boost performance in your app. So instead of getting everything from the database and then filtering here, why are we not filtering within the database, right? Like SQL was built for this. Let's have SQL do its thing. So one thing, side note, this isn't a database talk, but we want to make sure that we're not just passing the name in via string interpolation, because that could lead to problems with SQL injection attacks, right? If someone in their URL, instead of MotoG, tries a SQL injection attack, right, our code would be vulnerable. So we always want to be parameterizing our queries. And we want to await that, right? Instead of getting everything from the database and then filtering it in our app, now we're only getting what we need from the database. We're going to do the same thing with names, because look, it's doing the same thing. Wait, async. This is just going to return strings, right? Distinct name from phone info. Right? We're no longer getting everything from the database and then filtering our app. We're only getting what we need from the database. Less CPU spinning, doing meaningless work. That's exactly what this slide is about, right? Here we see another example, right? Instead of doing everything in your app server, you want to do it in the database server, because SQL is built for that. I chose Dapper for this because I wanted to make it clear what was happening in the SQL. I know Entity Framework is really popular in the .NET world, and with Link and everything, the lines start to blur about where things are being run. Is this filtering happening on the app? Is it happening in a database? Making it clear that, like, you want to make sure that things are happening in SQL, where SQL is the right tool for the job. And all that brings us to our next big problem, which is caching, right? As we all know, caching is one of the 3 hardest problems in computer science, along with naming things, off by 1 errors, and trying not to use this joke whenever you talk about caching.
Isn't that 4 things? Just joking.
I will take a sip of my water at this point. So what is caching? Just in case you weren't aware, caching is the act of saving a local copy of data. Why? So that you don't need to go retrieve it again or calculate it again, right? If you're doing some sort of heavy calculation, you don't want to do it more than once. Similarly, we don't want to be going out to the internet every single time to get the prices of this phone that we are interested in purchasing. We want to store that locally, right? Because it takes a few nanoseconds to get that from RAM, as opposed to from wherever these servers are located. Notice that we didn't talk about caching up front. We talked about it later on, because all these other things are important too, right? We want to make sure that our site is still fast, even if there's no data cached. We started off with, what, 27 seconds, right? So even if we have the data cached and it's fast, for the unlucky users who don't get that cached data, we want them to have a decent experience as well. Kind of this, along the same lines of the security paradigm of defense in depth, right? You don't just have a single point of security in your app. You want lots of different places. So in .NET, we have what's called a memory cache. It has the iMemory cache is its interface, and that's what we inject. So let's inject that in our app over here. We're going to be caching our HTTP requests so that we don't need to do them multiple times. So we add our memory cache. And then in our service, we want to add our cache, just like we added our HTTP client. We add our memory cache. We want to add the field for it so that we can use it. All right. Let's pull this out into a method so that we can hide it. Call it get response. So in here, right, we're creating our client, we're getting the response. We're going to wrap this in a method on the cache object called get or create async. The first thing we give it is a key of some sort. We're going to give it the URL as a key. And then it takes a method. Let's make this async since we have async inside. So inside this is when we do our work. And this work is only going to happen if the data is not in the cache. If the data is in the cache, we just return it from the cache. We want to tell it as well how long we should be storing it in the cache. If you don't have anything here, it's going to store it permanently, which is good in some cases. So we're going to say entry.absolute expiration relative to now. I know that's a very long name, but it's basically how long do we store it, right? I want to say an hour. So as long as our app is running, only go out to the web to get new prices at most once an hour. What did I break here? That. Okay. We're going to run our app, make sure everything works. Good. Okay, it wasn't too bad. Speed whiles, but notice every subsequent request is super fast. We're no longer going out to the internet to get these prices. We have the responses cached in our RAM. It only needs to go to RAM, which takes nanoseconds, not full seconds. So much faster, and I can refresh this as much as I want, right? So it's our caching example, right? Instead of doing a slow thing every time, we introduce a cache. We give it a key of some sort so that it's easy to look up. We still return the same thing, but we also add the expiration if we want. All right, this way we're not doing what's inside that async entry every time. We're only doing it when we actually need to get that information externally. How are we question-wise right now before we dive into the fun topic of load testing?
So Frank asked, is the process kind of what you showed for your regular kind of profiling process? Do you first sample really slow stuff, catch low-hanging fruit, or go line by line to try to speed things up? Like, I guess generally the question's like, is this kind of your regular process to profiling things?
Yeah, I like to start with a timeline because that gives a more visual representation of what's going on. And yeah, you don't get all the nitty-gritty details right away, but you can see, as we saw, like, okay, there's a whole bunch of white space or gray space happening. We've got lots of time when the CPU is just idle waiting for things to happen. Let's try and make it more efficient so that it's either doing more at once or doing something else while it's waiting.
Yeah, and I guess I would add too, it's like when it comes to profiling and trying to find problems, it's really more of an investigation. It's like, something's not right, but you're not really sure what it is right off the start. So usually there's not like a methodical process that works every single time, right?
Yeah, it definitely is as much art as science. And I like the investigation metaphor because I do often feel like I'm a detective about like, okay, what's going wrong? Let's search a bunch of different leads. And obviously I pre-prepared this so I know what the leads are and what comes next. But
Yeah,
Um,
I
there's
think
a
I've
lot more dead ends when you're doing it. When you're
yeah,
doing it in real life, or when it's a new app that you're not familiar with.
yeah, I think I remember somebody telling me it's like a murder mystery where you're probably the murderer, right? So
Yes, right. Especially if you're the one that developed it, like you're responsible for the code. And
yeah. Yeah, another thing I noticed, which is like really, to me, it's really impressive for you to show this, which is like everything you use has a cost and it's not magic, right? Like you showed that Angle Sharp, while it's a great open source library, might be a little behind in terms of the features it's using found in, say, .NET Core, and like the latest .NET 5 release. So there's kind of these hidden gains, and you shouldn't take for granted like the implementations that you're using, right? There's always
Mhm.
kind of something under the covers, and everything has a cost. So I kind of appreciate you showing that to the people watching.
Yeah, sure. And just for the record, with Angle Sharp, it is possible to use HTTP client under the hood. By default, it does not. um,
Yeah.
but yeah, there are lots, and especially in the past few years, .NET open source software is growing, and that's a good thing. There's more options,
Hmm.
which is a good thing, and
Yeah.
more of the community is getting involved, which is a good thing.
Yeah.
But we haven't gotten to the point of JavaScript where there's 20 options for any possible thing you could want to do, and you need to research them all and figure out which one's best.
Hmm.
So I think we're in a good spot right now.
Yeah, I
Um,
think so too. I think .NET is definitely getting better, and it's going in the right direction, at least in my opinion. So, other than that, let me see if there's any more. There are no more comments specifically, so let's continue.
cool. All right, so we're gonna kick it up a notch and start load testing our app. Right now that we are caching our HTTP responses and therefore not hitting these external services every time, we can feel more comfortable throwing more requests at our web app. We don't want to do that when we are calling external services every time, because that's, in a way, a denial of service attack. We're like, hey, get this page, get this page, get this page, get this page. Certain people could be not too happy about that. So we're caching it. We're only getting our pages once per hour now while the app is running, and therefore we can feel more comfortable load testing our app. Load testing, by the way, is the act of putting demand on a software system to measure its response, right? We're doing so manually, right? And when I was, refresh, refresh, refresh. That's one way of load testing. We're going to do this in a more automated fashion. Why do we do this? We want to observe how the system reacts to certain volumes of requests, right? Me hitting refresh repeatedly is only so much. We can do that much quicker in a more automated fashion, using anything from a for loop to there's an app that's been around forever called Work, W-R-K. There's a new fork of that since the original one's not abandoned, but kind of in maintenance mode. The ASP.NET team maintains a whole load testing. I would call it like enterprise load testing in their benchmarks repo. So if you're if you want to build that up in your company on your own, that's a great place for that. We're going to use something called Load Test Toolbox, which is something that I've been using for many years. It's still in kind of a pre-release stage or state. But yeah, I like it. It's kind of a happy middle ground in that it's simple to use, but it still gives some useful information. So let's actually show that now. So here I have any bash or terminal open, doesn't matter because it's .NET, right? Cross-platform now for the past many years. So we're going to .NET tool install global load test toolbox. And it's going to complain at me because it's already installed, but if you don't have it installed, it would install it. And we're going to call it with LTT, load test toolbox. It contains a couple tools, right? It's a toolbox. It has tools. We have a drill and a hammer. And these things do different things, right? A drill is going to send requests at a consistent rate. So we could say, hey, send 10 requests per second. And every 100 milliseconds, it'll send off a request. Hammer is going to send a whole bunch all at once, right? These tools are to test how your system responds to different things, right? A constant rate of requests versus here's 100 requests all at once, go handle them. So what we do, we can say LTT drill. That's going to give us, our options. What do we need to do to get here? So one thing I should point out is when you're load testing, especially when you're really starting to push the CPU of your web server, is you want the load to be generated on a different machine, because otherwise they're going to start competing for resources, the generating of the load and the handling of the load. So here, I mentioned my Raspberry Pi before, right? There's my local IP address. We're going to go to this URL. I forgot the parameter. We're going to say 10 requests per second. Actually, you know what? Let's start at 1 request per second, because we don't actually know how this is going to respond yet, right? We don't want to crash our web server because we could get too gung-ho early on. We're going to do it for 5 seconds, and we're going to output it to a PNG file. What's that PNG file? I guess we'll find out. So here we go. As it runs, it shows us our response times, right? So that's pretty good, around 100 milliseconds for each. We're going to then open up this drill, right? We can see a chart here. And this chart charts the responses over time. We only have 5, so the responses are kind of yucky looking. But we know that the system responded well to that, so we can increase that, right? Let's say maybe 5 requests per second for 10 seconds. Let's see how the system responds to that. It looks like our response times are still pretty consistent, so that's good, right? We can handle 5 requests per second. Note that our chart now has a little more information, right? We see some spikes. What are these spikes? What's going on? Let's push the envelope a little further. I don't actually know how far we can go right now with the current 20 requests per second. Looks like we're still good. So what you want to do when you're load testing is slowly increase that load until you find that you're starting to, okay, that was way too much. Until you're starting to see a problem, right? So we got, instead of less than 100 milliseconds, we now have responses in hundreds of milliseconds. And when we look at our chart, that's our old chart, we start to see more interesting things, right? We've got kind of 2 lines here. We've got this kind of upper line and we have this lower line. You can see they're both slowly increasing, and that's usually indicative of memory leaks. So we want to figure out what's going on here with that. One of the things to realize when profiling is that that act of recording what's going on takes a lot of energy. Not so much for sampling and timeline, but when you go line by line, it can be up to a 10x increase in time. So we're going to run our load test now against our app when we are profiling. So let's make sure that our page works, right? Looks good. You can see the second time is faster. That shows us that our cache is working. We're going to start recording. And because of that 10x increase, I'm going to knock this down again. All right, let's do 10 requests at 1 per second. And you can see, right, that the times take much longer. So when you're profiling, you want to take your response times with a grain of salt, because there's a lot more going on than just your app running. When we get our snapshot, we can take a look at what's going on. And we know that we made 10 requests, right? 1 per second for 10 seconds. So we could look at our number of calls again if we wanted to say, hey, what's happening a lot that should not be happening this often, right? Again, angle sharp is happening a lot. Maybe just like we cached our HTTP responses, we should be caching our documents that angle sharp is creating. That's actually a great idea. We should be doing that because, again, like look, as we scroll down here, angle sharp is responsible for so many of the calls that are happening. If we take a look at time, we can see that we're also taking a lot of time with our database calls. Maybe we should be caching our database calls too, because, 1 second from now, is our database any different? Probably not. So layering your caching is a good thing to do. And that's exactly what we're going to do next. I'm going to do that magically. It's the exact same as we did for our HTTP response, right? So our get all now, we're back in our phone service looking at our database requests. We're doing the same call as before, right? Our select all from phone info. We're going to cache it for a minute. A minute's fine, right? If the database is updated less than a minute ago, we're not going to get the new information, but maybe that's not super important for our use case. We're going to do the same thing with all our calls, right? Since all our calls are being called separately. And we're going to cache this too. When we are thinking of the key for this, right? This HTML string can be huge, right? Certain sites, especially heavy e-commerce sites, have responses in the hundreds of kilobytes. We don't want to be using that as a key, but what we can do is we can use the hash code of that, right? Anytime we get the same HTML, we know that the document's going to be the same. So that's exactly what we're going to do. Right? And actually, since, I'll do it this way, but we'll talk about it. Since we know that the same HTML will always return the same document, we don't even need it to ever expire. We can just keep it in memory forever if we want, right? We do want to clear it out probably eventually, but we don't currently care about that. So we're going to run this again. Now that we're caching all the things, well, not all the things, but we're caching much more now, so we expect a much faster response time. First request is always slow because we actually need to go out to the internet to get it. Second requests, third requests, all the subsequent requests are really fast. Great. Motorola has caught on and is now blocking me because I've been requesting the same page too much. Let's profile this to see what our difference is. And we're gonna load test it while we profile as well. So get the page once. Slow the first time, right? Extra slow because we're getting ready to profile. Start recording. We are going to, now that we're caching, I'm confident that we can bump it up to 10 requests per second. Yeah, look at those numbers. And this is with profiling running too, right? So let's check our snapshot and see what's next. Back in our plain list, which is where we get the most detail. get image data. What's get image data? Well, get image data is what gets this image. And we're doing that server side because this is something, obviously not a picture of a phone, but often, especially in the enterprise apps that I see, the image data gets put behind some sort of authorization request so that you can't just put in a URL and get someone's private document, right? You want to authorize that that document is only available to the people who are supposed to see it. So often you'll have responses rendered server side and then sent. So what we're going to do, right? We're going to make this async because right now we're waiting, right? We're saying, hey, go get this from the hard drive, which is where the image is stored. And I'm just going to wait for you to respond before I return. We want to be able to do other stuff while that happens, right? Great. So that's good. Now we can do other stuff while actually, I don't think our usage of this is actually async. Oh no, I'm giving away next steps. More Ryder is giving away next steps. Right, so I made that async. Great, so we're no longer busy doing what we want or doing something and then waiting for a response. We're able to do other things while it's happening. But what did we just do? We just asyncified our code, right? We made something async without changing anything else about it. Yes, we unblocked our thread, but is there a better way? Yes, there is a better way. In fact, HTTP and HTML together are the best tool for the job here. We could be sending a separate request for this image rather than embedding it in our request. So that's what we're going to do. And I'm going to do this the secret way again because it's getting late and I want to make sure everyone can go have lunch. So what we did was we have a new image method here, right? And we have our view is now returning this image instead of encoding the base 64 and putting it right there. So the app works the exact same way, but it's even faster because the rendering of the image has been offloaded, right, to a separate HTTP request. So we can see now, and again, because I'm just hitting F5 to refresh, right, you can't really see the difference is so fast, you can't see it as a single user, but this is where load testing comes into play, is that you can start to see it when there's multiple requests. So if we want to do this again, I'm going to bump it up 100 requests per second. How do you think we're going to do? Oh, still too much. I think what happened was this code does not have this cached.
I guess while this loads, the interesting point you made is like caches don't have to be long to be effective, right? And as you load test, yes, you could make your database might not be able to handle 100 requests a second, but it can definitely handle like 1 request a second, right? Just kind of
yes, neat. Yeah, yeah, and especially if unless you're doing some high-speed, stock market trading system, you probably don't need to the millisecond up-to-date data, right? Like having things expire with really short expirations should be totally fine. So here we go. We're down to less than 10 milliseconds on average, which is good. Not great, but good. I'm gonna speed through some of these next ones because they're kind of, at least the next one here is .NET specific. So we have dependency injection in our app, right? That's how we have things getting their dependencies, and they have certain lifetimes. We have scope lifetimes, we have transient lifetimes, and then we have singletons. What you want to do is be optimizing those to make sure that your dependencies aren't being created more often than is necessary, right? So we keep seeing angle sharp at the top of our list of, I don't want to call them offenders, but the things taking the most time. And a big part of that is that we are creating new instances of these things for every request. If nothing is changing between the requests, right, we can make them singletons. We can create one of them when our app starts up, and we can use that same one all the time. We can do this because there's no private data going on. We don't want to be spreading around other people's data potentially by giving them the same object that we gave someone else. We want to make sure that if anything is transient, that all the things using it are also transient. Otherwise, there's some confusion about the actual lifetime, right? So if we were to have a singleton phone service that uses the database, our database connection is transient. Well, it turns out that we only actually ever create one of those because the phone service is a singleton. So we want to make sure that, that the things that autocomplete is not happy. Wow, okay, I'm just going to type it out.
Actually, that gets me too. It's you either have to press return or tab. One replaces and one inserts. So
yeah, and my muscle memory is always tab. Right. So now we're not creating things as often, right? We're not instantiating our dependencies for every request. We're only doing it once. So that's going to cut down on the amount of time that we're doing. The last thing we're going to do, and again, I'm going to fast forward here, and we can take a look at the result, is that for every, where did it go? Oh, we're not there yet, right? So we're caching a whole bunch of stuff, right? But there's one thing we're not caching, and that's the end result. We have this get phone view model method that we're still calculating every time, right? We're not going out and retrieving new data every request. We're caching all that, right? Both from the database and from these external websites, but we're still doing the same work over and over again every request. And so we should really be caching that as well. So we can add our memory cache to this controller as well as the service that uses it. We'll add it as a field. And this all would have come out through our profiling, but I see it's 11:30 and I want to pick up the pace a bit. So we are going to then cache our instantiation of our phone view model. Pop. And we can say a minute, right? We can have our data be up to the minute accurate because we don't expect the output to change if the input is the exact same. So let's run this. Again, we're not going to be able to see the difference when we are simply loading a single page, right? The first time it needs to go get everything. Subsequent times it's much faster. We don't know how much faster, but we can see that with load testing tools, right? We're down to 3 milliseconds to 1, right? Now we can start to push it, right? If we do the mental math, we can say, if a request is taking 3 milliseconds, we could do technically 300 of them. Let's start with 100. And we can see that things start to get faster because there is stuff happening in the framework as well that's holding on to these. I don't know if we can do 1,000 requests per second. We can give it a try. Oh, we can. And look, we can start to see we're down to less than a millisecond. So we started at greater than 25 seconds, and we're down to less than a millisecond now, which is 25,000 times faster, which is, you know, a decent improvement. I'm happy with it.
You're a wizard, Steve. You're a wizard.
So the last thing we're going to do, and again, similar to caching, we don't want to have this be the first thing we do because it's not an excuse to ignore performance, is these have been running on .NET Core 3.1 the whole time. And we really should be running on .NET 5, right? It's the latest as of today. Again, I'm not going to YOLO .NET 6 while live coding. But if we upgrade this to .NET 5, you know, that's going to offer us a whole bunch of improvements for free. We don't want to ignore the actual work of making our app fast, but keeping your, we'll ignore that one. We talked about layering or caching. Keeping your dependencies up to date, especially with the .NET framework, because they have put so much effort into performance, that's going to allow your apps to be faster as well. Make sure this still works. I don't know how much more this is going to cut down our time. So it looked like we were 700 to 800 milliseconds or microseconds. Looks like a much more consistent 600, 700. So it looks like we gained about, I would say, another 10% simply by upgrading to .NET 5. So lots of stuff going on, obviously. You know, we made maybe 15 changes to this app and got it 25,000 times faster. We saw oops, wrong button, sorry. We talked about all this. We parallelized our work, right? That was the first thing we did. We were doing things completely sequentially, which is a waste of CPU and a waste of time. So let's send out all our tasks at once, get them all back. We want to make sure that we're doing stuff as well while our async code is running, right? We don't just want to be sitting there waiting for it to finish before we start. We eliminated duplicate effort. We optimized our database queries, make sure that things we're doing in SQL, that SQL was built for, we're doing in SQL, we're not doing in our app. We offloaded a heavy task to a new HTTP request. That's what we did with the image, right? HTTP and HTML are the best tools for the job there because we're on the web. Let's not, you know, reinvent the wheel by doing that on our own server side. And lastly, we cached multiple layers of data and calculations. No, we didn't just cache once, because if that cache misses, we want some sort of backup, right? We don't want 99% of our customers to get that nice, you know, 500 microsecond server time, while the other 1% get 30-second waits of where's the page, right? So that's kind of an overview of everything that we did. The slides and the app are available on GitHub. Everything's public. There's the URL. And I don't know if we were able to add these to the YouTube description after the fact, but we can do that. You can also check out Load Test Toolbox if you want to get it yourself. It's just .NET tool install Load Test Toolbox. I'm hoping for a 1.0 release before the end of the month. There's lots that still needs to be cleaned up with that, but things are looking promising with it, and I hope that can be valuable. I hope, you know, all these tools that I've given you, tools and techniques, are valuable. They can help you tackle performance problems you're experiencing. If you've tried everything here and still need help, if you need a hand getting started, if you don't even know where to start, I'd love to chat. Here's my info again. You can get in touch however you would like. As I mentioned, it's one of my favorite things to talk about, but it's also one of my favorite things to work on. That's why I'm trying to build a whole company around it. So thanks again for showing up. Thanks to Khalid and to JetBrains for hosting this. And I think at this point, we can kind of open it up to more general Q&A.
Yeah, there's not a lot of questions, but I'm imagining people's minds are just being blown by going from 28 seconds down to nanoseconds. So, microseconds, right? Microseconds. Like that.
Yes, didn't quite get into nanoseconds. I'm not sure that's possible yet. But yeah, I mean, there were a lot of different things that we talked about, and I'm happy that this is recorded because people can go back and kind of go one at a time, to look through each example and say, okay, how does this apply to what I'm working on? Obviously, the app that I built for this is, it's a demo app. It's not exactly real world. So, real business applications are going to look different. It's not going to be as obvious where the problems are, but they are going to look similar, right? The patterns are the same.
Yeah, it's funny looking at your code. It looks very similar to even enterprise applications I've worked on. So I'm sure those little problems are hiding in people's code bases and they're not really aware of it. But I think you said something really prescient at the beginning, is like you ended with those bullet points of what you did in this talk. But it's also important to remember that you should, and you said this at the beginning, you should make one change at a time so you understand that the change actually improves something, right?
Right.
So
yeah.
It's slow down to go fast, kind of.
Yeah, indeed. And testing is also important, right? There are loads of ways, especially, when you start doing funky stuff with caching, that you can actually break logic where it works without the cache, but it doesn't work with the cache. It works with the cache, but not without the cache. And
yeah, I think we've all been there. So somebody said thanks for rocking the session, Steve. So yeah, this is really awesome. So thank you to everybody who kind of stayed on through the whole talk. It was jam-packed with a lot of information. So other than that, let's kind of we'll shut down the webinar. It was a pleasure having you, Steve. I think this was by far one of the best talks I've hosted. So I'm really happy to have you on here. And anytime in the future,
quite the honor given some of the other guests I've seen.
Yeah. So anytime you have any thoughts, feel free to reach out. We'd love to have you back. Let me kind of wind down. So folks, thanks for staying with us. Thanks for watching. If you want any more information about any of the products that Steve was using to do his performance profiling, you can head to JetBrains.com. If you're specifically looking about information about Rider, you can go to JetBrains.com/Rider. Be sure to follow us on Twitter. We usually post tips and the latest news about our products there. And you can go specifically to our blog at blog.jetbrains.com/.net for the latest news and tutorials. Be sure to follow Steve at stevedesmond_CA and his website where he writes at stevedesmond.ca. So, finally, be sure to like and subscribe our YouTube channel if you like this content and want to see more of it. And thank you for joining us. So thanks, Steve, and thanks, everybody. We'll see you later.
Thank you all.